So, here you can see the global keyword. So, global is a qualifier which is defined in the CUDA programming model, and we have already discussed that this global qualifier tells the compiler that this function is to be run on the GPU. After that, we have another function, that is a main function, integer main, and within this integer main function I have written the another hello function, that is from the CPU. So, what are the function or kernel function we have developed? That function is to be launched using the kernel launch function, or you can say the kernel launch configuration. So, here you can see that the function name is same, what the function name I have used to define the kernel function. After that, you can see the 3 angular brackets, and in these 3 angular brackets I am passing 2 parameters. Here I am directly passing some numbers. So, first number is the number of blocks and second number is the number of threads, and because the function has is no attributes we have used. So, that is why during the kernel launch function I am not passing any attributes to it. And the synchronization function, you know that what is the purpose of synchronization is there, and we have already discussed the synchronization functionality, various type of synchronization functionality and various levels as well. So, now as per this program, my understanding is saying that because whatever the node is allocated to execute this program, the CPU is also available. So, CPU also must print its output like hello world from CPU, and but when the kernel function will be launched on the GPU, and I am informing the GPU that you should launch only one block and each block there must be a 10 threads. So, that means the GPU must print the hello world from GPU 10 times. This is my understanding is saying with this code which is written here. Now, let us execute this program with the help of slurp. So, first of all we have to compile this program. Source file, then -o to generate the output file. Now, just check output file is created or not with the help of ls command. So, you can see that one more file is added in my directory. So, that file is indicating it is a executable file. Now, I will use the slum script to execute this file. So, first of all I have to go to the script file which we have already developed. So, you have to change only the executable name here. After changing the executable name, you just save this script file and launch this script file with the sbatch command. So, now whenever you launch this command, one job ID has been assigned. So, we will see that whether some error or output file is created. Yes, output file and error file both are created with the job ID name. Check the error whether it has generated any error during the execution. So, there is nothing, that means the job has successfully completed. Now, we are going to check the output file. As I mentioned, we need some information to be printed. So, here you can see the output, the first line, because first of all the job is going to run on the CPU and then it will be called from the CPU. So, here you can see, as I mentioned, the first hello world we should get from the CPU, and after that when the kernel will be launched on the GPU, because we have already specified that there should be a one block and each block there are 10 threads. So, all 10 threads are working independently. So, all thread must return the hello world from GPU. So, output is as expected. If you want to play with it, you can change the number of blocks or you can change the number of threads in a source file. Again, after that you can compile it and you can execute. So, you can see the variation. Now, I will discuss the next program, that is floating point 64 and FP34 operation. So, first of all I will just explain you this program. So, you can see here the two global qualifiers I have mentioned. The first global qualifier is performing the FP64 operation. It operation supports addition and multiplication. You can see that is already mentioned in the if logic. Second global qualifier function, it supports the FP32 operation and it also performs the multiplication addition. The size of the data is same for both. You can see here total number of elements I am going to process here is 1024. So, in case of 64 you can see that data type is double, because double is required to store the 64 bit information, but for float type it stores the 4 byte. Space is required to store the FP32 elements. In next you can see the threads per block and blocks per grid. So, these are the two parameters which is always required to pass to the kernel launch function. So, I am just considering that each thread block has a 128 threads and grid per block is only 1. So, that means only one block will be mapped on one SM of the GPU. So, I have just printed some information about the size. So, it is optional. If you want to learn more about it, you can use that variable, otherwise learners can skip the printing the size of FP64 and FP32 variables. After that, you have to declare the memory allocation variables for FP32 and FP64. So, H is indicating the host. After that, you can see that I have used the malloc command. There are variables h underscore a, h underscore b, h underscore c and h underscore d. There are 4 variables for FP64 and all these variables I am allocating the space on the system's memory with the help of malloc command. Whenever I am talking about the system, it is a CPU's memory. Similarly, we are allocating the space for the 4 variables for FP32 element. After allocating the spaces, we are just initializing the value for testing purpose, or if you have any already data, you can use that data, you can load that data in this variable. Otherwise, we can randomly generate some value and initialize the initialize these variables. So far, we have done the initialization allocation in the system memory and initialization in the system memory. So, now we have to execute this program with the help of GPU. So, again we have to define some variables for the GPU. So, you can see here d underscore a, d underscore b, d underscore c. So, d is indicating the device. All these pointers are going to indicate the memory location in the device memory. Device memory means GPU's memory. After that, we are just allocating some space on the GPU's memory with the help of CUDA malloc function. So, 4 variables we have earlier allocated on the system memory for FP32 and FP64. Similarly, we are allocating the same size of space in the GPU's memory using the CUDA malloc function. Once the space is created, now the next step is to transfer the data, because whatever the data we have initialized, that is available in the host system only, it is not available on the GPU's memory. So, that is the reason we have to transfer this data from the host to device, so that GPU can access that data and perform the defined operations. So, you can see that the direction size, host to device. So, all variables for FP64 and FP32 is moving from host to device. After that, I have just added few events functionality intentionally, because I wanted to measure how much of time is being consumed while executing the particular operation. So, event we have decided start and stop, and we have decided elapsed time, and then we are starting the event and stop. After that, I am asking to record the start time whenever this just before the launch of the kernel, I am just initiating the CUDA event record, and then the count will start recording the time, the kernel will launch. So, just when the kernel will finish its operation, I am stopping the recording of time. After that, we have just synchronization functions, you can see, and we are finding the how much time is elapsed between the start and stop. The same thing as I have applied for the FP32 operations is as well. When these two operations are successfully completed, then I am going to copy the data back from device to host. So, important thing is that I am not here I am not recording the time for entire program, just like for allocation, deallocation and so on. I am just measuring the time when GPU actually perform the operation on the element. In simply, whenever the kernel launch function is executing, only that particular period of time we are recording here. So, after that, when the operation is completed successfully, so whatever the allocation we have done, we have to release the entire space on system's memory as well as on the GPU's memory. So, now we are going to run, and first of all we have to compile this program and we will run that. After that, we will check when we are performing the operation using FP64, how much time it will take. When we are performing the operation with the help of FP32 cores, then how much time it is going to take. So, program is compiled now. Now, we have to go to the same directory and we will check the binary is already created. we will go to the Slum script and we will just change the executable name here. Save and come out and launch the job with the help of sbatch command on the cluster. If you are not on the cluster, then sbatch command will not work. In case you have another cluster, another scheduler is available just like PBS or any other. So, you can study, you have to study those manuals to know that how to launch the scripts on that with the help of that scheduler. So, we are using the Slum scheduler. So, sbatch command is supported for the Slum scheduler only. Now, job has submitted and it has assigned me some unique ID, job ID to it. So, we will see that. So, it has created the output file and error file. So, we will just first check the error file. So, error file is empty, that means no error has been generated. Now, we will check the output file. So, here you can see that the size of double is 8 byte, we have asked to print this information, size of integer is also 8 byte. So, interestingly, now if you check the FP64 multiplication and addition time, so the kernel that was launched on FP64 cores, it has taken around 39.54 millisecond, but at same time FP32 multiplication kernel has taken only 0.05 millisecond to execute the same operation. So, reason is that, which I have already discussed, in each SM if you see there are only a few number of FP64 cores and FP32 cores are just double of the FP64 cores. So, you can go you can refer that particular lecture to understand, which I have already discussed about with the each process block of SM has only 8 FP64 cores and each process block of SM has 1632 cores. So, number of cores difference is first difference is number of cores of this reason, and second is the FP64 operations itself takes some longer time compared to the FP32. Now, we will go to the another program. We will discuss about any program SM execution count, program number 10. So, in this program you can see that again I have used the global qualifier, and apart from that I have used some assembly codes which I have embedded here, and after that I am performing some atomic operations of add. So, why this program is? So, I will just give you the simple example. I have intentionally mentioned here number of SMs. Suppose my GPU has so many of SMs, but I wanted to use only 40 SMs, and we know that we have already discussed that number of blocks is going to map on the SM. So, we have defined how many blocks we want to launch. We have requested 680 blocks, and physically we have only 40 SMs on which this block is going to map. To reduce the complexity, I have just taken that each block is going to run only one thread. So, how many blocks is going to map by the each SM and how many blocks is going to execute by the each SM, that I wanted to check. So, again I am repeating here, I have just make a limitation for this program, that I will use only 40 SM, and number of blocks I am going to launch is 680 is a software number, means a software things, but when I am talking about the SM, SM is a hardware entity. We know that each SM is always mapped on the each SM. So, intentionally I wanted to know here, if I wanted to launch 680 blocks and I have physically only 40 SMs, then how many SMs, then how many blocks is going to process by each SM. So, that is the purpose of this program. Learners can go through this program in a one by one manner, and they can try to understand what logic we have implemented here. But here we are just going to compile this program and execute this program. So, I am just going to change the executable name here. Submit the script, job ID is created, and we will see that whether error file is created or not, or output file is created or not. So, output file and error file both are created. So, there is no error generated. So, job has successfully completed. So, we just check the output file. So, here you can see that we have mentioned, we have requested only 40 SMs. So, SM ID is 0 to 39, and this SM ID we have calculated with the help of the assembly code which we have embedded in a program. So, you can see that SM0 is executed 7 blocks, SM1 has executed 6 blocks, SM2 has executed 7 blocks, and so on. This allocation of the blocks on the SM is being done automatically by the internal schedulers. Developer does not have any control over it, but you can see that each SM has working on multiple blocks. So, these are some programs I have discussed here, and if you see all the programs that is available, just go to the ls command, and you can see that there are some programs we have provided for the practice purpose. You can get this program, I am again repeating, you can get all this program by visiting the GitHub link, which we have already shared in the beginning, and right now we are also sharing. You can clone it in your directory and you can use these programs. So, in this CUDA course, we have developed some understanding about the architecture, CUDA programming model. We have understood that not only the CUDA, but there are other programming models are also available to program the underlying GPU. We have understood some concepts like memory layout, thread divergence impact on the performance, and whatever the concept we have discussed, for related to each concept we have developed some program. This program is available. So, learners can use these programs to develop their more understanding about the GPU. With this is the end of this course. Thank you.